In this video, I'm going to be showing you how you can build a team of autonomous AI agents to do work for you in the background. By the end, you'll be able to delegate work to these agents using a task management system in the same way you delegate work to just anyone else in your team. What I like about this approach is it allows you to have multiple tasks happening all at the same time without getting confused about what's going on. Most of us love the idea of having a team of agents working for us, but there aren't many easy ways to do that right now. Tools like OpenClaw are exciting and interesting, but I believe the architecture is relatively insecure because it requires you exposing things on the public internet. It's also a very complex project as well, with a lot of stuff you probably don't need. So in this video, we're going to take a different approach. We're going to look at a much simpler architecture that is really minimal and easy to understand, but it scales from one agent running on your laptop to potentially hundreds of agents running all at the same time. So let's get into it.
All right, so we're going to do a quick demo now. I'm going to show you how this all works. So we're using the linear task management system to delegate work to AI agents. It's important to note that linear is just for a demonstration. You could use this idea with any project management tool, Jira, Monday.com. You could even use this with a to-do list if you want. The general idea is we have a way of assigning work to an agent, and then the agent is going to pick up that work and it's going to move it through various lifecycle states. So when the agent first picks up a ticket, it's going to do its magic. It's going to run Claude Code or Codex to implement the changes, and then it's going to move the ticket to in progress. And then finally, when it's done, it's going to move it to a review status like this so that we can go and check that the work is okay. So I have a simple ticket here that I want to work on. So the first thing we're going to do is start up our agent worker. So I'm currently in the terminal now in the repo that we want to start the worker in. So the first thing I'm going to do is start the worker agent. This is going to be a worker that basically watches the ticket queue for new tickets. And when a new ticket becomes available, the worker is going to pick that up, move the status to in progress, do work by delegating it to Claude Code. And then finally, it's going to open a pull request at the end so that we can go and review the work. So let's go and start up the agent to begin with. You can see here the agent worker has now started and we're polling every 60 seconds. So what we want to do now is give it a ticket to go and work on. All right, so I have a bunch of tickets I want to work on. These are relatively small changes. So let's take this one, which is adding a variable to our interpolation. So we're going to go and move this to in progress. And then we're going to wait for the worker to pick up the ticket. So notice how we're just delegating in this model. We're not involved in the agent coding itself. We're no longer in the loop where we're sitting in the terminal waiting for changes. We're just delegating to our system. Our system is doing the work, and then we're just reviewing the output at the end. Okay, so you can now see that the agent worker has picked up the ticket. It's found the ticket, and it's claimed it by moving it to in progress. Now it's created a new Git work tree so it can go and make the changes. And you can see here what it's done is it's delegated that task to Claude. So Claude Code is now going to implement the changes, and then we're going to wait for it to complete. Just while we're waiting for the code change to complete, it's worth mentioning that you could run this worker agent anywhere. So this is running on my local machine, but you could run this on a virtual private server as well if you wanted to. You could run these workers anywhere, basically. So you can see now it's made the code changes. It looks like all of the tests are passing. So what we're doing when Claude Code makes the code change, we're asking it to review the code afterwards. And then we're marking the task as done. We're running a series of post checks afterwards. And then we've just opened a pull request. So you can see here the ticket is now marked as completed. So let's go ahead and check the status in the browser. Okay, so this was the ticket we just worked on. And you can see here if we go and open this up, this was the task that we delegated to Claude. It had quite a lot of instruction. And you can see here that the agent worker has commented on the ticket. It said that the task is completed successfully, and it's given us the last 50 lines of output from Claude Code. So you can see basically what happened. So if we go now over to GitHub, we should see that Claude has opened a pull request. Yeah, you can see here, this was the change we just made. So we can go and check this out. You can go and click here and see the files that were changed. You can see here, we're adding this additional variable. And we're also running a bunch of checks on GitHub as well. So CodeRabbit is a code review tool. I have this installed in Claude Code, but I also have it installed on GitHub as well. So this is doing an additional check. This is really important because we're no longer in the loop. We're delegating the work to agents. And so we need to make sure that our system is robust and it can handle making sure that the code is high quality. So the way we're doing that is to use a series of automated checks. All right, so you can see here that the checks are passed, so that we can now go and merge this code change. And it looks like we're now done. So what we did here is we completed a task, but we were not involved in any stage. We just delegated the task to the agents or the agent worker. The agent worker completed the task for us, and then we're just reviewing the output at the end. So now we can scale this. So we can have one worker working on one ticket, but we did say we were going to build an agent team. So the next step is to run multiple workers at the same time to work on multiple tickets. So let's go ahead and have a look at that. So going back to our task management system, let's go ahead and delegate some additional work. So we're going to add 2 more tickets. So I've got 2 bugs. We're going to add poll count and uptime to the log output. I'm also going to pass in this other ticket as well. Let's move that in. So now we're just waiting for the workers to pick up these tickets. Okay, so the agent at the bottom there has picked up the first ticket, which is gradient 132. So now this is working on a ticket, and we're just waiting for the top agent to pick up another ticket. So you can see here, the top worker agent has picked this up and it's delegated it to Claude Code. So now we have 2 workers working on 2 separate tickets at the same time. Okay, so it looks like the first task is now done. We're just waiting for the second task to complete. Looks like that's complete as well. So we're just waiting for it to open a pull request. Looks like both tickets are now complete. So let's go and double check. All right, so if we go to the review column, you can see here that this is the ticket we passed in, the magic numbers and the poll count. This ticket has been merged. We can now move this across to done. So these were the 2 tickets. You can see here the same as before, the agent has commented on the tickets. This one is done as well. So now we can obviously go and review these tickets. So what we saw here was the ability to run multiple workers at the same time, working on multiple things at the same time. Okay, so before I show you the code, I just want to talk through at a high level the general concepts here and how this works. So what we were demoing was a background worker, and the idea here is we want to find a way to delegate work to AI agents, but without being in the loop. We want to have a system that can scale to do work for us automatically. We can delegate work from our phones, from our browser. We're kind of working as managers here. We're just delegating work to agents who are going to do the work for us. And so the problem is that obviously most of us are using a coding agent in the same way. We're in the terminal. We're very involved. This is really, really useful. If you're working on something that's iterative or you're really having to go back and forth a lot with the agent, this is still the preferable way to work. You want to be involved heavily at all the stages to kind of iterate with the agent. But if you're working on smaller tasks like bug fixes or documentation updates, you generally don't need to be involved in the loop. You just want to hand these off to an agent and just trust that they're going to do the work. So tools like OpenClaw are similar to this. They allow you to do work in the background, but they're based on a different architecture. They're based on a push-based architecture where you're pushing things to webhooks. OpenClaw is also not specifically designed for this kind of work. It's a much bigger system and it exposes HTTP endpoints on your machines, which for our use case here is not desirable. So what we're doing is a different architecture. We have a polling-based system. So the agent worker is a polling background agent that watches your task manager for work, picks up tasks, and then executes the work. We stay out of the loop entirely. So we first create a ticket. The agent picks up a ticket, writes the code, runs tests, and then opens a PR for you to review at the end. As I said before, this is task manager agnostic. What we're demonstrating in this video is really the concept. You can make this work for any task manager. And task managers are the right way to delegate this kind of work, because if you have many, many things going on at once, you don't want to be chatting with agents. You want a way to actually track what they're doing. And that's the reason we're using a task manager for delegation. You would do the same thing if you were working in a team. You wouldn't delegate work via chats. You'd have some kind of system to track the work, especially if you're working on hundreds of tasks. It's going to get chaotic pretty quickly otherwise. This is also agent harness agnostic. So we demonstrated here with Claude Code, but this also works as well with Codex. Essentially, we're just delegating to an agent harness. It doesn't really matter which one it is. And so in terms of the architecture, we have 3 main components. We have the user here. So we're delegating by creating a ticket. As I said, linear, Jira, Todoist, whatever you're using. And then we have this agent polling loop. So it first runs a series of pre-hooks. The pre-hooks are deterministic code that can get run before you execute to, or before you hand off to Claude Code. Then we hand off to Claude Code or whatever agent we're using. The agent will then do its work, and then we run a series of post hooks as well. So these hooks can be used for basically anything, but a good example, we're using the post hooks to open a pull request using the GitHub CLI. You could run a series of checks, you could run tests, you can run linting, etc. In terms of the worker loop, it's pretty simple. We just pull the ticket queue, we claim a ticket, and then we just kind of work through this cycle. We're either going to be failed if we're not able to complete the task. If the tests are failing, we're going to mark the ticket as failed. Otherwise, we're going to move it to a done status. So perhaps the most interesting idea here is this difference between a pull-based and a push-based architecture. So a push-based architecture is how tools like OpenClaw work. So we have a HTTP endpoint. So this is typically a webhook endpoint or a gateway. And typically they expose that by exposing a port on your machine. So anyone can basically hit that endpoint. And so you have a larger attack surface, essentially. So with OpenClaw, you're exposing a webhook. When you're chatting with WhatsApp, you're sending a message to a webhook endpoint, which is publicly exposed. The architecture we're using here is a different architecture. It's a pull-based architecture. So we don't have to expose any ports. And so this is generally much more secure. We're not exposing anyway. There's no way for an internet actor to get into our machine at this point. We're only opening outbound ports. We're polling our task manager. The only downside is obviously we're sending credentials when we're polling, but otherwise we're not exposing any other attack surface. So this is better for agent work. Again, we have no exposed ports. We only make outbound requests. We have a simpler infrastructure. This is a really, really simple bit of software. It's not doing very much. It's really easy to adapt. It's really easy to understand. We're not adding layers and layers of complexity. This is really, really simple, but it scales really well. There are some minor trade-offs between push-based and pull-based architectures here. So push-based architectures generally will respond faster, but this doesn't really matter in our case because we don't really care about latency when we're working on a ticket. If it takes 60 seconds to pick up the ticket, it's absolutely fine in most cases. So just briefly talking about the hooks as well. So these are deterministic guardrails around non-deterministic agents. So we have a bunch of pre-hooks that we run. So this might be checking out a branch, doing a git pull. Then we have the non-deterministic element, which is running the agent. And then finally, we have these additional deterministic steps at the end. So this is an example of a pre-hook. You might want to check out a branch. And then a post-hook, you might want to run a series of tests. You might want to, push the task, which is what we're doing here. We're doing a git push at the end. And without hooks, we're kind of letting the agent loose so we can run a series of tests afterwards just to make sure everything works. And like I said, this pattern is nice because it scales really well. You can start with one worker running on your machine, but then you can scale up to have many workers running on many different machines. You could put this on a VPS as well, external servers. And it just scales really, really well. Okay, so I just want to show you the code quickly. So in our Claude MD inside the agent worker, we have a very specific workflow. So one of the challenges when we're delegating to agents in this way is we don't really have a way to essentially do an iterative process. So the way we're solving that here is to write the code to solve the ticket. We're running our tests to make sure there are no failures. And then we're running a code review with CodeRabbit. So this basically makes sure that we write the code, we review the code again to look for errors, and then we fix any errors that we find. This will reduce the number of iterations you need. Obviously, if you're delegating work in this way, you can't be back and forth as much. So you kind of need it to work in one shot. And then finally, we're running the test commands again, just to make sure everything didn't break. And here's an example of the configuration. You can see here we've got a bunch of hooks. These are just shell commands you can run before we invoke the agent. We have some pre-hooks and we have some post-hooks as well. We have the agent executor here as well, so we can do Codex or Claude, whichever you prefer. And then we also configure some other things like timeouts. But otherwise, this is just a relatively simple proof of concept of how you would build a system like this. If you are interested, I pushed up the code for this. Like I said, it's mostly just a proof of concept to demonstrate this idea of delegation to AI agents, but without being in the loop. So this is fully delegating work, not being partially delegating and being in the loop. This is full delegation. So it's kind of an interesting thought experiment to see how far you can kind of push these agentic workflows. If you are interested, this is the tool I'm using for code review. It's CodeRabbit. It's a great code review tool. It's an AI code review tool. You can integrate it with Claude Code. You can install it via CLI as well. But essentially, this gives you this extra layer of guarantee, which is really, really critical when we're delegating work in this way. Because we're not there sitting in the terminal reviewing the code, we need some kind of automated system to do that for us. And in this case, this is what I'm using. I'll do a video on AI code review another time, but this is a really great tool. It integrates really well with Claude Code. It's very easy to set up. So it's worth checking this out. So all of the code and documentation we discussed in this video is going to be linked in the description below. You can download it, check it out, do what you want with it. So hopefully you can see the power of this particular pattern. It's worth saying that all of the code and everything we discussed here is largely just for demonstration purposes only. You can take these ideas and build your own system. What's interesting here is the architecture, not necessarily the code. Hopefully you enjoyed the video. If you've got any comments or thoughts, let me know in the comments below. Thank you again for watching, and I'll see you in the next video. Take care.